Now we're coming back to the original motivations to consider definite integrals, which was to calculate areas of plane regions. So we're going to consider this kind of area. In other words, the area of a plane region that is bounded by two vertical lines, x equal a, x equal b, and two graphs, y equal f of x and y equal g of x, where one of the two functions stays above the other over the interval ab. So in that case, this red area can be seen as the area under the graph of f, so this white area, which is simply the integral from a to b of the function f, because here, at least on this picture, we have a positive continuous function, to which we take off this blue area, which turns out to be the area under the graph of the positive function g, at least on our picture, and that would be the integral of g from a to b. So for the red area, we obtain this white area minus the blue area gives us the red area. In other words, the area we're looking for is the integral from a to b of f minus the integral from a to b of g, which is simply the integral from a to b of the difference f minus g, where f is a larger function. So to put that more formally, the area of the region bounded by these two graphs and two vertical lines x equal a and x equal b, where f and g are continuous functions, so that we can consider integrals with no problems, and the function f stays above the function g for all x in the interval ab. This area is going to be given by the integral from a to b of the difference f minus g, where f is larger than g. Now in this argument, this geometric argument that we gave, we used the fact that the two functions f and g are positive functions, so that we can interpret integrals as areas under the graph of the function. However, you can see that this is completely inessential, because if I move up or down both function f and g by the same quantity, it's not going to change the difference f minus g, and therefore the integral f minus g. So we can assume the functions to be positive, because if they were not, like here, of course this integral is the same as the integral we've seen before, where we move everything up by the same quantity for f and g. Just like that. So now that we've seen how to calculate this kind of area bounded by two functions and two vertical lines, let's look at some examples. Starting with the area of the region bounded by y equal x squared plus 1, y equal x, x equal 0, and x equal 1. For this kind of problems, the first thing you need to do is make a sketch, even if it's a rough sketch, to see which function is above the other on the corresponding interval of x values. The x values to consider for us in this case are between 0 and 1. And here are our two functions. We have a parabola x squared plus 1 and a straight line y equal x. And the area that we're looking for is bounded by the two vertical lines and these two graphs. In other words, this is this red area on the picture. And according to the consideration we have seen on the previous slides, this area is simply the integral from 0 to 1 of the function above, which is x squared plus 1, minus the function below, which is x. And this is easy to calculate. Because we have a continuous function, we can use the fundamental theorem of calculus. So all we need is an antiderivative. An antiderivative of the function here is x cubed over 3 minus x squared over 2, that's antiderivative of the negative x, plus x for the antiderivative of 1. And we evaluate that between 0 and 1. At 1 we get 1/3 minus 1/2 plus 1, which simplifies as 5/6. And at 0, of course, we get 0. So the area here is 5/6. Of course, the unit for that is unit squared, or whatever u is for the unit of length on each axis. Let's look at another example, where we're looking for the area of the region of the plane that is bounded by the two curves y equal x squared and y equal 2x minus x squared. This is of slightly different nature, because in this case we are not given the equation of the two vertical lines. So again, first thing we should do is sketch the graphs. Of course, we have for y equal x squared a parabola that opens upward. for y equal 2x minus x squared, a parabola that opens downward. And so we get this kind of pictures, and this is the area that we're looking for. So to write out the integral, we should first find the coordinates of these points of intersections of the two curves in order to know on what interval of x values we should integrate. The picture, of course, suggests here that these points of intersection should be x equals 0 and x equals 1, but if we were to look for that algebraically, to find the intersection points, of course you want to find for what x value you get the same y value on both curves. In other words, you set 2x minus x squared equal to x squared and solve for x. So if we put everything on one side, we get 2x minus 2x squared minus 2x equals 0. And factoring out 2x, we see that this happens when x is 0 or x is 1, which corresponds to what we can see on the picture. In other words, we're going to write out this area as an integral where x ranges from 0 to 1, and we integrate the function on top, which is 2x minus x squared, minus the function at the bottom, which is x squared. So we integrate from 0 to 1, 2x minus x squared minus x squared, that is 2x minus 2x squared. Using the fundamental theorem of calculus to calculate that, we only need an antiderivative. Antiderivative of 2x is x squared, of 2x squared is 2x cubed over 3, and we need to evaluate that between 0 and 1. The value at 1 is 1 minus 2/3, that is 1/3. The value at 0 is 0, therefore the area is 1/3. Now let's say we want to find this area that is enclosed between the parabola y equal x squared minus 4x and the straight line going through the origin and through the point of coordinates 6, 12. Well, in other words, this line going through the origin, going through the point of coordinates 6, 12, has slope 2, goes through the origin, so it has equation y equal 2x. See that x ranges from 0 to 6 for this area, and therefore the red area is obtained as the integral from 0 to 6 of the function on top, which is 2x, minus the function x squared minus 4x, which is below. That simplifies as 6x minus x squared, that we integrate from 0 to 6, so all we need is an antiderivative. An antiderivative of 6x is 3x squared, of x squared is x cubed over 3, and we evaluate this function 3x squared minus x cubed over 3 between 0 and 6. The value at 0, of course, is going to be 0. At 6, we get 3 times 6 squared, so that's 3 times 36. And then 6 cubed, I can see that as 6 times 6 squared. And the 6 over 3 is 2, so I get 3 times 36 minus 2 times 36, so this is just 36. And this is the value of this area, the unit being just whatever unit of length we use, squared. Let's say that now we want to find the area of the plane region bounded by y equals sine x, y equals x equal pi over 2, and x equal pi. As usual, the first thing we should do is a sketch of these graphs to see which one of these graphs is above for this interval. So this is what it looks like, and if x ranges from pi over 2 to pi, then this is the area we are talking about, comprised between these two vertical lines, x equal pi over 2, x equal pi, and these two graphs, y equals sine x and y equal x. You see that y equal x is a function above, and therefore this area is obtained as the integral from pi over 2 to pi of x minus sine x. An antiderivative is x squared over 2 plus cosine x, and we have to evaluate that between pi over 2 and pi. The value at pi is going to be pi squared over 2 minus 1, because cosine of pi is negative 1. And the value at pi over 2 is going to be pi squared over 4 over 2, so that's pi squared over 8. And cosine pi over 2 is 0. So that simplifies as 3 pi squared over 8 minus 1. Again, the unit would be just the unit of length squared. One more example. similar to the one we've seen with the two parabolas, one opening upward, the other one downward. We're in the same situation here. We're looking at the area of the plane region enclosed by the parabola opening downward of equation y equal 12 minus x squared, and the parabola opening upward of equation y equal x squared minus 6. As usual, we want to make a rough sketch of the graph in order to see what we're doing. So this is going to look like that, and on the picture it looks like the points of intersection have x-coordinate -3 and 3, but this is something we can calculate explicitly. So we're looking for this area between the two curves. We need to know the x-coordinates of the points of intersection of the two curves, and to do that we want to know for what x we get the same y value along both graphs. In other words, we set 12 minus x squared equal to x squared minus 6 and solve for x. Putting everything on one side gives us 2x squared minus 18. I can factor 2, I get 2 times x squared minus 9, which factors further as x minus 3, x plus 3, which confirms what we have seen on the picture, that the points of intersection have x-coordinate -3 and 3. What that means is that this red area is obtained as integral from -3 to 3 of the graph that is above the other on that interval, and that's 12 minus x squared, minus the graph that is below, which is x squared minus 6. Simplifying, we get the integral from -3 to 3 of 18 minus 2x squared. But that's an even function, so the integral from -3 to 3 of 18 minus 2x squared is 2 times the integral from 0 to 3 of 18 minus 2x squared. And graphically you can see that, of course, the y-axis is an axis of symmetry for this red area, therefore we can just calculate half of it by taking the integral from 0 to 3. This is not really important. We could take just one time the integral from -3 to 3, it just simplifies a little bit the calculations. So an antiderivative of 18 minus 2x squared is 18x minus 2/3 x cubed, and we evaluate that between 0 and 3. And after simplification we obtain 72 for the value of the area. Now turn to the next video to see what we can do if the curves intersect more than once over the interval of x values that we're considering for the area.